For my research project, I studied superconductors, looking to answer the question, can energy really be transferred without heat loss? First, a little background. What are superconductors? Superconductors are a material which can conduct electricity with no electrical resistance when its temperature is at or below a certain critical point. A superconductor is usually metal or another element. There are two properties which characterize superconductors while in their superconductive state. One, they offer no resistance to the passage of electrical current. When resistance is zero, current can circulate inside the material with no energy loss. And two, if the magnetic fields of the magnet are sufficiently weak, they will remain on the surface of the superconductor and not penetrate it. When the weak magnet comes close, its fields are pushed away, and the magnet hovers over the superconductor. This is known as the Meissner effect. There are two types of superconductors. Type 1 can be penetrated by a magnetic field if it is strong enough, which ruins the superconductive state. This can be explained by the Bardeen-Cooper-Schrieffer theory, known as BCS for short. The particle makeup of a superconductor is known as the lattice, and electrons move inside the lattice. Two electrons together are called a Cooper pair. The lattice contains protons, which flex as the Cooper pair moves through, creating a distortion. This distortion moves the electrons through the lattice without any friction. A Cooper pair can be broken up by thermal energy, so the superconductor must remain at a very cold temperature. When the temperature reaches a certain point, the magnetic field of the magnet will penetrate the superconductor, causing the superconductivity to come to an end. Type 2s are a little bit different. These superconductors are able to be penetrated by the magnetic field, but still keep their superconductive properties. Within the material, there are areas of superconductivity and non-superconductivity, explaining why the magnetic field can penetrate the superconductor without harm. Type 2 superconductors allow for superconductor usage in high magnetic fields, and they even led to the development of particle accelerator magnets. Now, why do we care? As of now, superconductors only work at very low temperatures, under negative 315 degrees Fahrenheit, or under negative 193 degrees Celsius. This is a problem, because it is not realistic to cool materials down to those low of temperatures just to act as a superconductor. The BCS theory does not explain any sort of high-temperature superconductor, and if you remember, the Cooper pairs in type 1 superconductors, as well as the entire superconducting state, can be destroyed by a significant enough rise in temperature. When a high-temperature superconductor is discovered, the game will change immediately. The discovery of a superconductor that works at higher temperatures will help many industries. The medical industry, for example, uses superconductive magnets in MRI machines. These magnets have to be chilled, and the chilling is very expensive. In the communication industry, more telephone calls and internet activity can use a superconductor line compared to a regular communication line. Electric providers would benefit as well. There would be no thermal energy loss in their lines. For example, an average of 7% of energy is lost to heat on the power lines from the hydroelectric generators at Niagara Falls to a power station in New York City every day. And numerous cities around the world can take advantage of magnetic levitation technology, known as maglev. This transit technology provides a drastically faster ride time compared to regular shuttles, buses, taxicabs, or other methods of transportation. Some cities around the world already have maglev transportation today. This is my model. It is a maglev shuttle showing how superconductors can replace the wheels and eliminate friction on the tracks. Because there is no friction, there is no resistance, and thus there is no heat loss. There are magnets on the corner of the shuttle car, and the track itself is also magnetic. The two are the same polarity, thus resulting in a hovering effect. By cooling the track magnets to around negative 450 degrees Fahrenheit, the magnetic field is around 10 times larger than ordinary magnets and electromagnets, strong enough to suspend and propel a train. There are electromagnets on the sides of the C-shaped track, and similar to the protons, pulling towards the electron Cooper pair as they pass through the superconductor lattice, the opposites attract and pull the shuttle forward. The magnets on the side of the shuttle go with the magnets on the side of the C track. The like poles repel, and this pushes the shuttle forward, just like how the shuttle can be pulled forward by the opposites. And finally, here are my citations.